Welcome, dear friends. So the plan of the lecture today is to derive certain very basic expressions for entropy change using the property relations. So what I plan to do today is I would be deriving first the property relations, and then making use of this property relations I would go to the derivation of entropy change relations applicable for ideal gases. Okay, so this is a plan, and let me start first by writing the first law of thermodynamics, first law of mathematical statement applied to closed system. So what is that statement? What is that mathematical expression for first law of thermodynamics? Can anybody tell me? First law of thermodynamics applied to a closed system. First law of thermodynamics applied to a closed system. Any answers? Am I audible? Okay, Sairaj, correct. So the first law of thermodynamics as applied to the closed system is Q. Okay, or let me write it in differential form. Let me write it in differential form. Okay, Sairaj, you are correct. I understand that you are not in the position to use symbols while answering this question. Okay. So let me write the first law of thermodynamics in differential form. Q is equal to du plus dw. Okay, this is first law of thermodynamics, right? And this system, whether it is any system, this would be applicable. If you go for a closed system now, this is applicable to any system. Let me write down, this is applicable to any system, closed or open, and applicable to any process, reversible or irreversible. Okay, but if I want to consider a special case of closed system, you know that closed system, the work would be the PdV work. Okay, work would be the PdV work, and hence the first law of thermodynamics, the mathematical statement of first law of thermodynamics, can be written as del Q, is equal to du plus PdV. Okay, this is the first law of thermodynamics applicable to the closed system, right? Now, so let us call this as equation 1, and this equation 1 comes from the first law. You also know from the second law that ds, from the second law we had defined a property called as entropy, and you know that ds is dq reversible upon t. Okay, dq reversible upon t. It means that your dq is del q, right? So del q. Okay, so the del q is basically TDS, and let us say equation 2, and this comes from the second law. This comes from the second law. Okay. And what I do is that, because my aim is to derive the property relations by combining the first law and second law, so I would be substituting the value of dq as TDS in equation 1. Okay. So from 1 and 2, from equations 1 and 2, which is a combination of first law and second law of thermodynamics, okay, I get a third relation, which is TDS. TDS is equal to PdV. This is an important relation. TDS is equal to du plus PdV. Okay, this is an important relation which is going to be very useful in deriving the expressions for entropy change of gases also. Okay, so this is first property relation. We will call it as property relation 1. Property relation 1. Okay, TDS is equal to du plus PdV. TDS is equal to du plus PdV, or in other words, DS is equal to du by T plus PdV by T. Okay, so just remember this, that TDS is equal to du plus PdV is one property relation which we have derived. Okay, I hope it is clear to you. Okay, is this clear? Yes or no? Okay, thank you, Gargi. So now let us go to the second relation, which is also called as a property relation. This property relation, so let me erase this. I hope, can I erase this? Can I erase this? Okay, thank you. So I'm erasing this now, and keep in mind that what we have derived is a TDS relation. TDS is equal to du plus PdV. And how did we do that? Just by applying the first law of thermodynamics, okay, and the second law of thermodynamics, that is del Q is du plus PdV and ds is del Q by T. Using these two equations, we got the first TDS relation. Okay, now I am erasing this thing, and I will write the second TDS relation. Okay, so the second TDS relation I will be deriving by using the property called as enthalpy. So enthalpy, by the definition of enthalpy, this is U plus flow work PV. Okay, U plus PV. This is by definition of enthalpy. Why it is so? It is just defined. If you see the terms like U and PV coming together, instead of calling it as U and PV, okay, separately, you have another term called as enthalpy. So that is only the meaning of enthalpy. There is no other meaning, physical meaning to it. Okay, so H is equal to U plus PV. So if I differentiate this now, so it becomes DH is equal to du plus PdV plus VdP. Okay, right? So this is what, from the first law of thermodynamics. Now let us call this as equation some 3 or whatever. Let us call this as equation 1 again, whatever you call it as. You know that du plus PdV from the first law of thermodynamics is del Q. Del Q is du plus PdV from the first law of thermodynamics. So instead of del Q, I would be substituting this, instead of du plus PdV, I would be substituting this as del Q. So del Q plus VdP becomes my equation. Now, from the second law of thermodynamics, del Q is also TDS. Okay, so this becomes TDS plus VdP, right? Or in other words, the second TDS relation becomes TDS is equal to, just rearranging these terms, DH minus VdP. Okay, so this is the second TDS relation. This is the property relation 2. That is the second TDS relations. What was the first TDS relation? This is a property relation 2. The first TDS relation was TDS is equal to du plus PdV. This is the first TDS relation. Okay, so we would be using this TDS relations. This is the first TDS relation. Now to obtain the first TDS relation. Okay, so TDS is equal to du plus PdV, right? TDS is equal to du plus PdV and TDS is equal to dH minus PdP. So these two TDS relations we would be using, okay, we would be using for finding the property of entropy change, for finding the entropy change for ideal gases, right? So remember these two equations and we'll go to the entropy change relations. Okay, just before that let me just comment on this PdV and VDP. Okay, if you look at this TDS is equal to dH minus VDP, right? And if you consider, for example, flow system a flow system, okay, so this is U1 plus P1 V1, or let us say this is enthalpy at H1. Okay, and this is U2 plus P2 V2 at the exit, that is enthalpy H2. Okay, uh, let us say that the heat transfer is Q, okay, and the work is W, work obtainable is W. Okay, neglecting the changes in kinetic and potential energy, so you can write it as the steady flow energy equation. The steady flow energy equation becomes H1 plus Q is equal to H2 plus W. H1 plus Q is equal to H2 plus W. Okay, or in other words, H1 minus H2 plus Q is equal to W. Okay, now Q is TDS and this is DH. Okay, minus DH. So this minus DH plus TDS is equal to, let us say in the differential form, del W. So if you compare this equation, okay, if you compare let me rewrite this in the form of TDS relation. So TDS is minus DH. So TDS is plus DH minus. Okay, so just have a look at this expression. So if I call this as equation 2 or A, and if I call this as equation B, equation A and equation B, if you compare this two, what you'll get is this is TDS minus del W plus V. So you will get basically, what I mean to say is that you would be getting a expression of work for the, you will be getting an expression for work for the steady flow system. Okay, steady flow system. It means that this TDS relation also helps us to appreciate that the work, okay, the work which we are talking about, the shaft work which we are talking about, in case of flow processes or open systems, that can be obtained as VDP work. Okay, so this is the flow work which we were using earlier for getting the derivation of work transfer in different processes which we discussed. Okay, so let us forget this for the time being. We are now using these TDS relations. We are now going to use these TDS relations for obtaining the entropy change, for various processes. Okay, for various processes. First, I will derive the generic expression for entropy change for ideal gases using these TDS relations, and then we would be looking at the specific cases. Okay, so now for the time being, just note down that TDS is equal to dH minus VDP, TDS is equal to dH minus VDP, and TDS is equal to du plus PdV. Okay, so let me erase this now and let me derive what I would be deriving now is the entropy change of ideal gases generic expressions. Okay, so I'm clearing this canvas and I would be deriving now the generic expressions for entropy change, entropy change, entropy change. It's a good idea that you have a notebook with you and you do the derivation. If you're not tired, okay, then it is a good idea that you have a notebook with you and just go on doing this derivation along with me. Okay, so that you would comprehend this better. Okay, so what is the starting point? The starting point is that two general property relations. Okay, so we would be using two general property relations. One is TDS is equal to du plus PdV, and second is TDS is equal to dH minus VdP. Okay, now you know from the definition of specific heat at constant pressure, dH can be written as CpdT and du can be written as CvdT. Okay, this you must understand. Okay, this you must understand, right? I am taking here small u and small h, which means specific internal energy and specific enthalpy. Okay, meaning that per kg, right? So we can rewrite this. For example, I can rewrite this expression as, I will be rewriting this expression as ds is equal to du by t plus pdv by t. So this property relation I have rewritten, right? And then I would be substituting the definition of internal energy, that is cvdt by t, cvdt by t. And because you know that per kg pv is equal to rt. Okay, so it is v is equal to p by t is equal to r by v. P by t is equal to r by v. Okay, this would give us this p by t is equal to r by v. So this I would be substituting here instead of p by t. I would be substituting this as r by v dv. Okay, I hope this step is clear to you. That what I had done is, let me just repeat what I had done. This is the property relation I am using, property relation 1, TDS relation 1. TDS is equal to du plus PdV. Mind well that this is small u per kg. Okay, so TDS is equal to du plus PdV, which is same as ds is equal to du by t plus PdV by t. So du, that is the differential change in internal energy, by the definition of specific heat is CvDT. So instead of du, I have substituted the value as CvDT, and this P by T from the gas equation, general gas equation, P by T, I have substituted as R by V. P by T I have substituted as R by V. Why? Because PV is equal to MRT, M is 1, so PV is equal to RT, so P by T is equal to R by V. Okay, so this ds becomes Cv dt upon T plus R upon V dV. Okay, so if you integrate now this between any two processes, let us say from 1 to 2, what you will be getting is S2 minus S1 is equal to CV ln, that is log to the base e, ln T2 by T1 plus R ln log to the base e V2 by V1. So this is one important relation which you can use for calculating. You can use this relation for calculating the entropy change. This equation you can use for calculating the entropy change during a process. entropy change of ideal gases, okay, during the process for both the open system as well as closed system. Okay, this is one expression. So now when you will be using this equation, you will be using these equations if you know the temperatures and if you know the volumes. Okay, then if you know the initial temperature, final temperature of the process, if you know the initial volume and final volume of the process, then you can easily get the entropy change during that process by this equation. Okay, similarly what I would be doing now is I would be deriving the another expression which would be equivalent of this another equation for entropy change of ideal gases, but now I would be using instead the second TDS relation. I would be using instead the second TDS relation. Okay, so allow me to do this derivation now. Okay, so again what I would be doing here is I would be rewriting this equation property relation 2. Okay, I would be rewriting the property relation 2. Okay, and this I would be bringing the entropy change expression on one side, that is I will be dividing the expression by T. So this becomes obviously dH, again I am talking about specific enthalpy here, upon T minus VdP upon T. Okay, dH by T minus VdP by T. Okay, again using the same trick, that is the definition of dH, specific heat. So dH is equal to CpdT. So instead of dH, I would be using Cp, not Cv now, mind well, because it is enthalpy. So it is CpdT and not CvdT. So CpdT upon T, CpdT upon T, and then again by using this relation, PV is equal to RT. You know that V by T is equal to R by P. Okay, so instead of V by T, I use R by P, that is R dP by P, R dP by P. It means that this H, instead of that H, I am putting it here CpdT, and instead of this V by T, I am substituting this as R by P. Okay, this one, this term, R by P. Okay, so now again you must have guessed that I am now integrating it. So integrating, what you would get is S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. Okay, P2 by P1. So this expression which I got, you can understand that this expression can also be used for finding entropy change of ideal gases. This expression can also be used for finding the entropy change of ideal gases, right? So this expression, when to use this expression? So obviously when you are given the temperature, initial temperature, final temperature, if you know the initial pressure and final pressure, then this equation becomes handy. It comes handy in getting the entropy change. Okay, so it just you understand that all these equations, okay, they are relevant. Okay, and you need to just choose a better equation depending upon what are the given parameters. Okay, doesn't mean that one equation would give you the wrong result. Okay, because you know that all these properties are related by the different laws of ideal gases. Okay, you can rewrite this equation. For example, I can rewrite this equation by substituting the value of R as Cp minus Cv, and what you will get is, you can just try this. Doing this, you will find that you will get a very interesting thing. Cp ln T2 by T1 minus Cv Cp ln T2 by T1 minus Cp CPLN P2 by P1 because instead of R I am putting here Cp minus Cv. So P2 by P1 and minus minus plus, so it becomes plus Cv ln P2 by P1. Okay, so this is another expression which you have got. Okay, which is same as if you look at this, same as Cp ln V2 by V1 plus Cv ln P2 by P1. Okay, so these are the expressions which we can use for entropy change of ideal gases, right? I hope it is clear to you. What we have done is we have now obtained the expressions for entropy change of ideal gases, very generic expressions for entropy change of ideal gases, by making use of the property relations. And which are the property relations we are using? One property relation I am using is TDS is equal to du plus PdV, and other property relation I am using is TDS is equal to TH minus PdP. And what are these property relations? These property relations are nothing but the relations obtained by combining the first law of thermodynamics and second law of thermodynamics, the mathematical statement. The property relations are just a combo expressions of first and second law mathematical expressions. Okay, first and second law. So these equations you would be using while solving the numericals. Okay, and in order to appreciate this, then how do we use these relations? I will be taking one numerical. So take down one problem now. I hope that you have copied down this derivation, and hence I will be now going towards the numerical. So write down the numerical. Can I erase the board now? If you have copied it down, can I erase the board? Okay, thank you. So thank you, Kunal. Let me erase this, and I hope that you have copied down these expressions. And let us now solve a numerical. Okay. So copy down the numerical now. Come on. A ideal gas undergoes a thermodynamic cycle. Okay. The question is, ideal gas undergoes a thermodynamic cycle. Undergoes a thermodynamic cycle. So when you are saying a thermodynamic cycle, it means that there are a set of processes which should get you back to the initial state. The meaning of thermodynamic cycle is there are 2, 3, 4, whatever number of processes are there, which would get you back to the initial state. Okay, so thermodynamic cycle, and this thermodynamic cycle consists of consisting of three processes. So first process is, let us call this as process 1 to 2. Process 1 to 2, and this process is the constant volume heating. Constant volume heating. First process is a constant volume heating. Okay, from the initial state, that is P1, which is given as 0.1 megapascals, and T1, which is given as 15 degrees centigrade, up, and V1 is given as 0.02 meter cube. This is heated up to a pressure which is P2, heated up to pressure which is P2, which is 0.42 megapascals. Okay, this is the process 1 to 2. Then it is given that there is another process. You need to copy it down. Okay, the problem I will be erasing it, so you need to copy down this question. So process 2 to 3 is now a different process. This was a constant volume process. Now the second process is a constant pressure process. Okay, and this is a constant pressure cooling. So this is a constant pressure process now. and process 3 to 1. Okay, process 3 to 1 is given to be a different process, but this different process is a constant temperature heating, that is isothermal heating. Okay, isothermal heating, and it is said that the initial state is regained, and it is said that the initial state is up to the initial state, that is up to state 1, up to the initial state. So draw this cycle on a pressure volume diagram, and you can write it, also draw it on the temperature entropy diagram. So let us first draw it on the pressure volume diagram. Draw this cycle on a pressure volume diagram. First you draw the process 1 to 2 on a pressure volume diagram. I want you to draw the process 1 to 2 on the pressure volume diagram. So how would that look? The process 1 to 2 on a pressure volume diagram, how would that appear to us? The process 1 to 2 on the pressure volume diagram, how would that appear to us? Yeah, correct. Right. You are right, Gagi. Anybody else? Process 1 to 2 on a pressure volume diagram. Ritesh is also correct. So obviously, process 1 to 2, as Gargi and Ritesh are saying, they would be it would be a vertical line on a pressure volume diagram, and because it is a constant volume process. Okay, so I have not drawn it vertical. So let me try drawing a vertical. I'll be using another pen here. Okay, so let us say this is 1, this is 2, and this is heating. Okay, so the volume is V1 initially, and hence the volume, because it's a constant volume process, so obviously V2 would be how much? V2 would be how much? How much would be V2 if it's a constant volume process? So V2 would also be 0.02 cubic meter. Yeah, correct. So V2 would be equal to V1, that is 0.02 meter cube, right? Right. So first let us find the entropy change during the process 1 to 2. We'll go step by step. Find the entropy change. Find the entropy change during the process 1 to 2. Process 1 to 2. Find the entropy change during the process 1 to 2. And tell me the answer. So first thing is, what you should do is, you need to find yum, okay. Yum P1 V1 by RT1. Now P how much? 0.1 megapascals. 0.1 megapascals means it is 100 kilopascals. Mega means 1000. 1000 into 0.1 is 100. Okay, so 0.1 megapascal is 100 kilopascals. So P1 is 100 kilopascals. V1 is 0.02 meter cube. So 100 kilopascals into 0.02 meter cube. Right, the gas constant is 0.287 kilojoules per kg Kelvin into temperature. You need to be very careful that temperature always needs to be converted into Kelvin. Okay, so the temperature would be 15 plus 273. 15 plus 273. So tell me the value of yum. How much is the value of yum? And once you get the value of yum, now you can find the value of T2 also. T2 by T1 will be equal to P2 by P1. Why? Because the volume is constant. Applying the gas equation, volume is constant. So using this, you can also find T2. You can find T2 and then you can find the entropy change using the generic expression. Okay. So whatever method you use, you can use any equation and just make sure that you are obtaining the correct value. Okay. So maybe I can also use this equation, the entropy change. What is given to me is V1. So I can use this equation like S2 by S1. This is constant volume heating. So if you remember our first expression here, S2 minus S1 is equal to CV ln T2 by T1 plus R ln V2 by V1. Okay, and this term becomes 0 because V1 is equal to this becomes 0 because V1 is equal to V2. Okay, so you are left with a very simple expression here, that is this is m. Okay, it means m CV ln T2 by T1. So this would give us the entropy change during the process 1 to 2. Entropy change during the process 1 to 2. So what is the value of m you have got? What is the value of m you have got? The value of m, how many kgs you have got? The value of m. Yeah, Kunal, you are right. Kunal is right. Anybody who has got the value of m? So it's a good idea that you use your calculator. Gargi, check the value of m. There is some mistake you have done. Kunal has got the answer right. See, it's a good idea that you use your calculators and do the calculations. Yeah, Neha is right. Kunal and Neha got it right. Anybody else who is taking some pains in using the calculators? See, everything is written on the board. You are just supposed to use the calculators, nothing else. Aditya is right. All right. I hope that you understood the calculations. So if you put these values, then you will get a value of m as 0.0, approximately 0.024. Zai is also correct. Ganesh, Zai, all. Thank you. So now once you get it m you have got in this equation. So you have got the value of m. CV, you know, CV is how much? CV is CP minus R. Okay, CP minus CV is R. So CV is 0.717. Or if the values are given in the numerical, for example, in this numerical actually, they had given you the value as CP is 1. So we know that CP is 1.005, but suppose it is given that CP is 1, and suppose they are giving you R as 0.187. So you know that CP is R. So which is nothing but you will get CV is equal to 1 minus 0.287. This way. Okay, so if the values are given in the numerical, you might use those values instead of using the standard values. Okay, that you have to keep in mind. So I would be using the value as 0.717. The value of m I know is 0.024. Okay, and then T2 by T1. So the T2 value is 1210. Garge is right. So the T2 value is 1210 Kelvin. Okay. So putting this T2 as 1210 and this value of T1 as what was that? T1 was 288, I guess. 288. Okay. You would get the value of entropy change. This is the first part. Whether the entropy would increase or decrease, what will happen to the entropy, whether it will increase or decrease, and why? Yeah, why it would increase? Why would it increase? It will increase because the gas is being heated. Okay, so along with the heat flows the entropy. So when the gas is being heated, the entropy of the gas would increase, right? So the entropy change value, anybody has got the value? How much is that? Okay, Ritesh has got it. Ritesh is right. Ritesh is right. So the value of entropy change in the first process is 0.0246. Okay, and what would be the unit of that? The unit of that would be what? What would be the unit of entropy change? What would be the unit of entropy change in this? Ritesh, what would be the unit? Anybody who can tell me the unit? The entropy change unit? The entropy change would have the unit kilojoules per Kelvin. Okay, kilojoules per Kelvin. Okay, this is not specific entropy change. It is capital S. It is not small s, because we are including m into it. Okay, right, Ritesh. So, kilojoules per Kelvin. If it was small s, then it would have been kilojoules per kg Kelvin. Gargi, it is wrong. It is not kg per Kelvin. It is kilojoules per Kelvin. Kilojoules per Kelvin. Okay, that is the entropy change during process 1 to 2. Now represent the process 2 to 3 on a pressure volume diagram. Now represent the process 2 to 3 on a pressure volume diagram, and how would that appear to be? How would be that process looking? And what would happen to the volume? Yeah, Ritesh, you are right. And what would happen to the volume? What would happen to the volume? It would be a horizontal line, as Gargi and Ritesh are saying. Yeah, it would reduce, right? So you are right, Gargi. The volume would reduce and it would be a horizontal line. Why would the volume reduce? Because it is cooling. Okay, it is a cooling process. So the representation, so let me represent this on the pressure volume diagram, the next process. So that process would look somewhat like this. Okay, so now use the appropriate relation and find the change in entropy during the process 2 to 3. Okay, during the process 2 to 3. So I'm erasing this first part of the problem. Okay, and or let me erase the top portion. Please use your notebooks instead of simply listening passively. If you participate in actual solving, that would be a fun, and that would also give you better insights in what we are discussing. Generally what happens is that if you simply listen, after some time our attentiveness is lost, we feel sleepy. Okay, there is boredom, and once you feel sleepy and lose an important point, then you fail to understand the subsequent points. So it is always a good idea that whatever we do in the classroom, same thing you can follow here by using a notebook, though there is nobody to supervise you, but the self discipline is good. So if you want to really enjoy the lectures and understand those, so it is a good idea that you participate proactively. Okay, so we would be using if you remember the second expression which we had derived, the TDS, using the second TDS relation, I had derived the expression as follows: S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. This was the expression I had derived. So now it is the process 3 to 1, 2 to 3. So instead of 2, I would be writing 3, and instead of 1 I would be writing 2. Okay, so S3 minus S2 would be Cp T3 by T2 minus R P3 by P2. But you know that we are talking about a constant pressure process. So constant pressure process means P2 is equal to P3, and hence this term, the second term, would be 0. This term would be 0. Okay, so you have a very simple expression now, and because I want to include also capital S, so the expression would be mCp ln T3 by T2. So you already know what is M. You know the value of Cp. You know the value of T2. First find T3 and then find the entropy change. First find T3 and then find the entropy change. How will you find the value of T3? How will you find the value of T3? Any guesses? How will you obtain the value of T3? So the value of T3 we will be obtaining by using the general gas equation, that is P2 V2 by T2 is equal to P3 V3 by T3, and because the pressure is constant this would go off. You know the value of V2, you know the value of T2. Okay, and hence you also know the value of what you know. Yeah, and you can also find it like this. P3 V3 is equal to MR T3. Okay, so V1, right. So V2 by T2 is equal to V3 by T3. That would give us the value of T3. That would give us the value of T3, and hence you can find the entropy change. So tell me the value of entropy change now. Tell me the value of entropy change. Enough hints have been given to you. Enough hints have been given to you. Also note that, okay, so what is the entropy change? Anybody is getting this? Entropy change? Find entropy change. Let us see who is getting the answer. It is negative you are getting. Obviously, you would get it negative. What is the value you are getting, Kunal? 0.006. Just check. I don't have the answer with me is different. I have not solved it. Kunal, just cross check. Kunal, your answer is different than the answer which I have. What is the value of V3 you are getting, Kunal? So T3. Kunal, what is the value of T3 you are getting? Tell me the value of T3. Temperature T3, Kunal. 1209. How you got 1209? T3. You are cooling the gas, right? The temperature is different. The temperature is not the same. There is basically a constant pressure cooling. Okay. So the temperature would be less. What is that temperature? You assume the temperature to be same. So how will you find the value of V3? Can you find the value of V3? No, Kunal, just cross check your answer. P3 is equal to MRT3. Okay, P3 V3 is equal to MRT3 and P2 V2 is equal to MRT2. Right? So you tell me the value of T3. Tell me the value of V3. What you get? The temperature is wrong. You are cooling it. You are cooling it. So how will you find that? So you must get this answer. I want you to solve this at home and I'll just write down these answers. This is the answer you must get, and this the other answer is S1 minus S2. Okay. So these are the answers with me. I want you to apply your mind, and in the next class we will discuss this. Okay, the entropy change during the process 2 to 3, the value with me is 0.0344 kilojoules per Kelvin. We cannot solve it actually. We don't know the intermediate values. And the value for the entropy change during the process 1 to 2, which is the isothermal process. I will be doing that process over here. This is the process which I am drawing here. It is isothermal. That value you must get is at 0.0099 kilojoules per Kelvin. Okay. So if you get the answers, you can email me. Okay, and we can discuss this also if you want. So thanks for being online and have a good day. So this is left as a homework for you to complete. The answers are given to you. Use the expressions which we had derived for getting the answers on entropy change. It's very simple. You are just to apply the gas laws, nothing else here. Thank you.